All right. In the previous video, we discussed how to implement queues in a theory format. Now we'll be implementing the code. But before doing that, I just want to update the stack code that we have written. So there are three things that I want to update. The first thing that we are having a typedef in the next line, but we actually don't need to do that. We can actually create a typedef over here and name it as a pointer-based typedef and have that stack over there. Okay. So what this is doing is we are creating a typedef of something called the structure of stack. And the definition of the stack comes over here. And we're creating a typedef to not the structure of the stack, but the structure stack's pointer. And hence we're having this pointer over here. And stack is the name of the typedef. And then the other updates that I wanted to do in the malloc function, since I told you that it will be returning void pointers. Here, the stack is of the pointer integer star. And hence we'll have to return int star over here. And I didn't do it. There are some opinions about this kind of typecasting from malloc functions. People sometimes say we shouldn't do that, but I was taught this way in school, so that is how I'm doing this in the course. All right. And coming to loops, I don't think we are having so many big numbers involved in our code, so I don't think having an int over here is so necessary because it's just a waste of space over there, allocating 4 bytes of memory. So I'll just go with a short. And that too, having register as a storage class for the short variable will also make it a lot quicker compared to normal variable. Okay. So I'll have register short over here too. Okay. So yeah, that's it. These are the three changes that I wanted to tell. And now we'll be shifting into writing a queue data structure using arrays. Okay. So let me create a new file, queues and queuearray.c. As we already know, we have 4 includes, one for input output, other for booleans, other for the dynamic memory allocation functions, and another is the limits. Cool. And we also have a macro defined for us called the queueempty, and it will be just the int min. We'll be creating a structure called queue, and we have similar to that, we have an array called queue. And this time we have 3 variables because in a queue, we just don't have a single running pointer called top or something, but we have 2 of them. One is the front side of the queue and another is the rear side of the queue. And as usual, I'll be having a max size thing too. Okay. Now, instead of creating a typedef to this struct queue in another line, since I've just discussed how to do that, I'll just do it over here and I'll name it queue. All right. With a small queue. That rhymes. Okay. So we'll be creating our queue constructor. All right. And it takes in a max size. And we are going to create a structure variable, a pointer based structure variable to the structure queue. And since we'll be doing it using malloc, we'll have to typecast it into a struct queue star, which is an alias for queue. And the size of it will be just the size of the structure queue because that's a variable of the structure queue. So that is how we dynamically allocate the memory, which will be, by the way, since we're, as I've told you, we'll be allocating 20 bytes of memory for this over here. Is it 20 or 16 bytes of memory? But I think another integer over here. So it will be 14 plus 4, which will be 18. And even 18 is not a multiple of 4. So hence, yeah, again, it will be just 20 bytes of memory. Okay. Now, as we know, initially, the queue will be having both of its running variables as initialized to -1. I think this should be rare. All right. And of course, actually, first things first, we'll have to have max size as the first over here because, yeah, And since the array is not a stack-based array and we are using dynamic memory allocation, I'll allocate it using the malloc function. And since the number of elements that will be present in the array will be just max size number of elements, and size of each of them will be the size of an integer because it's an integer array, we'll be doing that dynamic memory allocation over here. And the analogy that I've been doing with the stack, that I'll be returning the queue and I'll be using the same memory that I've allocated for this in all the other functions. All right. So this is the queue constructor. Now, I just want to have a demo array maybe over here, just so you know, we have 1, 5, 2, 4, and 3. Okay, so this is the, let us assume this is the queue. So we'll take this as an example whenever we want to get back to a queue and all. So the first function is we'll have to create some utility functions first, because we'll be using these in other important functions. First is empty. So since you know that front will be at -1 and rear will be at -1, we can check for both of those conditions and only then tell that the queue is empty. But at times rear cannot be at -1, but front can be at a -1. So that is possible. So we'll be just having return queue of front equals to -1 as a condition for is empty. Okay. So if you know that the front pointer of the queue is at the index of -1, that means that the queue is empty. All right. Now it gets quite tricky when we are getting into is full. I've seen many implementations of the queue data structure which have got this function wrong. So I'm just going to make things clear here for you. Okay. So let us assume that, okay, let us also say that front equals to initially -1 and rear equals to initially -1. So these are the variables that we get. Since I've inserted 5 elements into this queue, we know at the first insertion, we'll have to update not only just the rear, but also a front. So basically the concept of queue, as I've already discussed in the theory video, rear variable increments every time we are having an queue function or pushing something into the queue from the rear. And the front pointer increments when we are dequeuing something or popping out of it. So it's not like we'll be having a single variable and we increment it while we add something and decrement it while we take out something, like in the stack data structure. But here we'll be having 2 pointers and we increment both of them according to the operation that is being done. Okay. So the front updates when we are deleting something and the rear updates when we are adding something. And queues get quite nasty to understand when we are having the first element to insert, because only at the first insertion, we also have the front increment. It's only the rear that increments every time that a new element is being inserted, but the front variable also increments to 0. Since if the first element is getting into the queue, that means the front is already at -1. It will get to 0. So you hardly see these both variables equal in value, because that will be an edge case for queue. And for example, we are having 5 elements as of now. So rear will be -1 to 0, 0 to 1, 1 to 2, 2 to 3, and 3 to 4. Okay, so the index will be at 4. But F will be at -1 to 0, and it will be 0 and not at -1. After the first insertion, we'll be having the front variable at -1. And after the remaining insertions from then on, we won't be incrementing the front, we just will be incrementing the rear. Okay, now the value of rear is 4 and the value of front is 0. Now let us assume that I've deleted 2 elements from here. All right. So now I just have these 3. So since I've deleted twice, this will be 0 to 1 and 1 to 2. All right. Now let us assume that I've deleted all of this. So I've deleted 3 times, and you can see front being deleted 2 to 3 and 3 to 4 and 4 to 5. Okay. So this is what happens. You can see that the front variable, which should always be behind the rear, because take a real world queue as an example, and you can never have the front of the queue exceeding the rear end of the queue, right? That is never possible. Okay. And I'm talking if you're taking the queue from this to this. So this is the front and this is the rear. Okay. You don't get confused. Don't get it the other way around. So hence, when you see that the front variable is equal to the rear, or front variable is getting more than the value of that of R, that means that is called as the queue condition. And we'll have to check for that condition every time we are popping something out of the queue or dequeuing something. All right. So the is full condition, people think that since queue of rear is what will be getting updated every time. So people think that if that is equals to max size -1, that is just, the condition is full. All right. But you can see the max size of this queue over here is 5, and you can see R is 4. So we'll be thinking that 5 minus 4, these both are equal, and this queue is full, but oh, see, this is empty. So we'll have to check for F2 while we are checking for the is full conditions. So it's not only just Q is equals to 1 minus the max size of the queue, but also that the queue front should not be more than or equals to 0, and mostly it will be equals to 0, because it can't be at -1 while we are having R at any other value other than -1. Because if at all R changed at least once, that means the queue is also changing, because at the first time we are inserting something, R moves and hence F to F moves too. So this is the ideal condition to check for if the queue is full or not. It's not just checking for the rare, because rare doesn't update when we are deleting each and every element in the queue. It's the front that is updating. So we'll have to check if even this is true. All right. Now that we have the utility functions updated, I have another function here called getSize. All right. Yeah, I think I didn't implement it inside the stack data structure. So I'll be just doing it after having it over here. Okay. So first, we should be pessimistic. If the queue is empty, and you know that we'll be passing that to over here, I'm going to return a false. All right. No, wait. I'll be returning a 0. That means the size of the queue is 0. There are no elements. All right. Now, if there are any elements in the queue, that means the queue of rare, which is the rare end of the queue, which is an index, by the way, minus queue of front, which is also the front end of the queue, which is an index, by the way. So if we just subtract those both, we'll be getting the value of the size of the queue. But this is wrong, because you should keep in mind that whenever the queue is inserting its first element, f also increments by 1. Like this thing over here, that f increments for the first time while we are inserting something, this completely changes the game in every function that we implement when it comes to a queue. Hence, we'll have to decrement -1 over here. All right. So yeah, you get habituated to it when you see the implementation of a queue while we run it. Now we are getting into the most important function, which is enqueue, which is inserting something into the queue. And the first parameter will be the queue itself. And next comes the element. Being pessimistic, we have the is full condition. We can't insert something into the queue if the queue is already full. And we are going to return a false. Now let us say, from here things get quite tricky. Okay, so let us assume that the queue is empty. What is the first thing that you're going to do? So it's if the queue is empty, what are we going to do? We're going to do 2 steps. One is to increment the rare variable and also the front variable, because as I've already told you, only for the first time while we are doing enqueue, when the queue is empty, that means that is the first time obviously when the queue is empty, we'll have to update both of these variables. And inside the actual queue array offers, we'll have to insert in the new rare position. All right. So this is like just the push operation in the stack. All right. This is it. Else, what are we going to do? If the queue is not empty, assume that there are 3 elements in the queue. What is for example, I want to insert another element into the queue. Then I'm just incrementing the value of the rare over here, right? And it gets to 5, right? And here we have, for example, a new element called 6 or something. Okay. So we're incrementing rare over there. Okay. So we'll just do these things, but not quite exactly the same, because we'll not be incrementing the front if the queue is not empty. And we'll have this over here. Now, this is quite a long number of code, and we'll have to return a true, because as I've mentioned, enqueue operations and push operations, at least how I code it, I just want to return a Boolean. If we are able to push into something, then we'll be returning true, or else we'll be returning false. Okay. Now, you see, we can just reduce this logic into 1 or 2 lines. This is like too much. Like, find what are the common things that you're doing in these 2 operations. We're incrementing the rare and we are putting that value in both of these. So why don't we just take it out of this if else group, because that is exactly what we are doing in both of them. So I can just delete it from here. So even if this condition is satisfied and it gets over here, or if it gets into there, in both of these, this will be implemented. And similarly, even this happens too, right? Even this happens. So we don't even need an else clause over here. Okay. And you also know that since we are just using the prefix operator, I can do this over here instead of writing it in another line, because it first increments only at the new position of the rare now, then the element will be incremented. All right. Now that I'm doing that plus rare in the else block, I've just removed it. I can remove it from here too. And this is the only thing that we do. Okay. So increment rare and assign the new variable. This is just that stack kind of push thing, or the enqueue principle of any data structure. But for the first insertion, the front should also be set to 0. Okay. Some people like to do it this way by making it so specific that we are setting it to 0 and we are not just incrementing it. You can go whatever you want. Okay. Because it's always set to 0 if it is the first time we are doing it. Okay. Cool. So this is that cute little function. Then we have bool dequeue. Okay. By the way, if at all you saw this somewhere, it's not dequeue, it's called a deck. Okay. So it's called a deck. We spell it like that, and we have comparisons to a deck of cards and all. So it's a kind of queue. It's a double-ended queue. That is why we call it DEQ. And yeah, I'll be explaining that in this series too. All right. So for the dequeue operation, we have our queue, and we should be pessimistic. We have is empty to that queue, and if that queue is empty, we can't delete anything from that. So hence we'll return a false, as I've already mentioned. For example, let us switch these two over here. So this will be at 5 because while we are dequeuing something, we're just incrementing the front to its next value. You see that front being more than the rear, and I told you that this is called the queue condition, right? So we'll have to check for that on every deletion. I've already mentioned that. So what we will be doing over here is we'll have to check for that queue condition in every dequeue operation and in every poll operation that we'll be doing. Okay. So here, if the value of the front is exceeding the value of the rear, that means we got a problem. And what we do is something peculiar. We call it resetting the queue to its initial values. So here we just take this and add the values of -1 to front and rear. That is exactly what we have in the constructor. So we reset the queue because front can always will be more than rear only if the queue is empty. Okay, so possible only if the queue is empty. Hence, we don't have anything already existing in the queue, so we are not screwing up any things that are stored in the queue, so we are not damaging anything. So what we're doing is just resetting its values to -1 again, so it will be just like a fresh new queue, and we won't be having any errors. And now that the dequeue operation is done successfully, we'll be returning it true, and that's it. So this is the dequeue function. All right. Now we have two little functions over here because it's like stack is having one main special index called top, and we have the peak function for that to check what is at the top. But queue, we are having two ends over here, one for insertion and one for deletion. And I thought it'd be a great idea to have peak functions for both of them. All right. Now you can't peak for any element in the queue because the queue is empty, and we'll be just returning queue empty over here. Remember, we are not having booleans over here. We can't return a false over here. We're returning the value. We'll have to return that queue empty, as we have already discussed that. Okay. So I have queue and queue of front. Okay. So this is the value of the array which is having index called front. Now I'll have a very similar function called peak rear, and I'll just do some vscode break over here. All right. And that's done. Boom. Okay. I just use Control D to select both of them, the both instances of that. All right. So we have peak rear done too. Now comes the poll function, and we don't have two polls, okay? Because polling is just dequeuing, but we are all returning the value of the front element. All right. So it will be like peak front plus dequeue, and we are not having anything related to peak rear in there. So we'll have the queue, and what we are going to do is similar to any other operation. We'll have to first check if the queue is empty or not. If it is empty, we can't delete anything from the queue and return it too, and hence we can't do that. And okay, let's get this straight. All right, what do we want to do? We'll have to do what we did in the dequeue operation, right? So what we'll do is we'll just copy things until there and paste it over here. Okay, so we are incrementing the queue value of the front variable, and we are checking if queue condition is being violated, and if it is being violated, we are resetting the queue, and that's all normal, right? Now we want to return a number, which is the value of the before deleting or before polling from the queue, what is the value of the queue front? So what we can do here is to store internal variable called result, and we can return that result. Now in the poll operation, when it came to stacks, I was not storing it in some variable, but I'm using the postfix operator and all. But I can't do that over here because return statement is a final statement, and I can't have this if condition after the return statement. And you might be thinking, why even have that if condition after the return statement? Let us have it here. But you see that it'll be okay if the front value is not greater than rare. Then I can just do that q front plus using the postfix operator and it works. But if at all this poll operation is making the queue empty, like it is deleting the final element, then we see that the front will be greater than rare and it will be reset and it will be -1 and the 0th element will be returned, which is not possible. All right. So we'll have to first store it in the result variable and we'll have to return it. We have no other choice. Cool. So we're done with the poll function too. We're done with all the mainstream functions. Now we just have a contains function, which I think I'll be copying it. Even the print function, I think, because I don't want to spend so much of time rewriting the same code that I've done. And I'll paste it over here. Stack. Limiting. All right. You know what? We'll just do F2 over there and put a queue. This will be the queue. And we'll have to send it there for the queue. And it starts at queue front and it goes till queue rare. All right. And we'll be having it incremented. Because I don't want to do it in reverse this time because that is not needed. Because in stacks, since we are using the n over here, we'll be doing that. But since queues are even thought of using a horizontal method and not as a stack in a vertical method, I'll be having a tab over here instead of /n because I don't want the printed statements one after the other, but I want them tabbed so that I can see them real queue like this. All right. Like how a real queue exists. Cool. Now I have that, get the queue is empty, or it goes from front to the rear. Now what if I want to do this? We'll take the queue. And if the queue is empty, we are retaining the queue empty because we can't check for the key if the queue is empty. And I'm having starting from queue of front to queue of rear. Okay, so it starts from the front to rear. It's not like the one end of the data structure is fixed, which is 0 in here, because both of the ends will be moving from -1 to whatever number. So we'll have to start from front and we'll have to go to rear. And I'm using not just the decrement, the less than operator, but the less than equal to operator, because even rear is a index. So the queue of that index should have the key. Now let us have a main function and let me create a new queue using the queue constructor. And I'll pass in 5 over here. That's great. Now let me have the enqueue function and I'll be passing that queue and the number 5. And let me pass in 6 number system because in the previous video we have been doing just those numbers 4 and 2 and then 3 and then 6. Okay. And I guess I'll just click on so. So I'm saving it. I hope there are no other errors. And just before implementing it, I just want to implement this method called get size even in the stack. All right. So it's just that I don't want it to be 0, or else we just return stack of front, we have stack of top. Okay, so now this is the trick. We have top over here, but top is the index and we want to know the current size of the stack. And you know that if there are 5 elements in the stack, the top variable will be 4. And if there are only 2 elements in the stack, the top variable will be plus it will be 1. And hence we'll have to add 1 over here. You just don't need to iterate through the stack and everything. You can just do that. And you don't even need this over here, if I was correct. Because example, if the stack is empty, it will be at -1 and -1 plus 1 will be 0, which is exactly that the stack is empty. All right. So yeah. Cool. Now we have this and the queue function. Let us just implement it and see. I did Control plus B. We are compiling it. Yes, we have that. We are running it now. And I have 5 and I have some error. Okay, so I figured it out that if the queue is empty, we're doing something. But if at all the queue was not empty, because only the first time, I'll just go through the code, okay? So what I'm doing over here for the first time while I'm inserting something in the queue is empty. All right. So what happens? It comes to the enqueue function. It comes to this function. It goes to if it is full. Of course, it is not full. And it comes to if it is empty. Yes, it is empty. It sets the front to 0 and it decrements rear to 0. And at the 0th position, we have the element which is 5 and returns a true. Boom, done. And the next time another value, for example, 2 comes over here, it is not full and it is not empty, and hence it just returns and the insertion is not taking place. So the bug that I have in the code is that there is only one thing that we have to do, and that is queue of front equals to 0, and the remaining should be out of that if condition. I remember deleting all the other statements, but I forgot to indent these back to their normal position. All right. Now we're going to compile and run it all over again. I should have debugged that process. All right. So I have 5 and 5 after 1 and 1 after 4 and then 2 and then 3. But I don't have a 6 because 6 can't be inserted, right? Now let us check for another function. We'll just do a poll function in between, maybe after this. All right. So you can just print the poll function just like that. It's a %d. It's an n over here. It's an n over there. Poll element. We'll have that. Let us check. I'm compiling it now. So 5 will be inserted, 1 will be inserted, and 4 will be inserted. And the polled element is 1 because that is that a bug? Hell yeah, it is a bug because I'm just storing this over here, but it should be the value of the queue. So result is not just the index here, the value that is present at the front. Okay, so I'll have to be doing that. So in the poll function, I'm storing the result somewhere, and after doing that, then I'll have to increment the front, because every time we are dequeuing something or polling something, we'll have to increment it, and we are storing it as the result. And since we can't do that after the if condition, we are not returning this all over again over here, because it can be reset if the queue is getting emptied in this poll function, and the result variable will be just doing it. It's good to have bugs this way because you can revisit the code and have some clear explanation and understanding of what is going on and everything. Now we see. So the first element, the front side is 5, and hence the polled element will be 5, and the front variable is just incremented. So we have 1, 4, and then 2, 3, 6. And 6 will be inserted because we are deleting something, and hence the max size condition is not getting violated. Okay, so you can just check all of the functions if you want. I'll just now peek the front variable, because now the front variable the front value can't be 5, it should be 1, right? So it'll be like front element, and it should be n. So it should be 1. Peak front should return a 1. Yes, it is returning 1. All right, so that's good. So that's it for this video, and in the next video, we'll be going through linked lists. So till now, we've discussed about array-based data structures. We are using arrays and, the inbuilt C programming arrays that we are having to construct some abstract data types called stacks and queues over that. We'll be restricting the operations that can be done over arrays to single-ended or double-ended values. And in the node-based approach, we'll be just creating those building blocks of those arrays. Like in every array, we'll be having a combination of integers. So instead of having combination of integers, we'll be having combination of nodes, and node is just another structure which is not only having an integer but also other properties associated to it. So it's like a custom container, and those containers will be put into a stack or a queue in the later part. So we'll be just dealing with linked list, and then we'll be implementing the queue and the stack using those linked list. All right.